In the fourth lecture of this chapter, we are looking to the measurement of aircraft airspeed. By definition, airspeed is a relative velocity between the aircraft and the air mass within which it is flying. Basically, the latter is the wind speed. Okay, airspeed is a key aircraft performance parameters because the aircraft aerodynamic forces are a function of the airspeed, and we can see the lift is related with v square, and also the drag is related with v square. And there is another terminology called ground speed, and ground speed is a relative velocity between the aircraft and a fixed point on the ground. For example, we have a reference like the house or human being, whatever it is, and we see the aircraft is flying, so the speed of the aircraft is called the ground speed. Okay, and what's the relation between the airspeed and the ground speed? And if we add the wind speed, so I'm showing a cloud as a wind speed, so the airspeed is a ground speed minus the wind speed in this scenario because they are in the same direction. The ground speed and the wind speed is with the same direction. If the wind speed is against the ground speed, against the aircraft, so the airspeed would be the ground speed plus the wind speed, depending on the wind speed vector. And the next question now is how do we measure the airspeed? And it's based on the Bernoulli's equation. And we can see the first term, PT, is the total pressure, P is the static pressure. And on the right-hand side, half rho V square is called the dynamic pressure. We actually have seen this Bernoulli's equation in aerodynamics or fluid mechanics. Okay, so we have the airspeed now V equals square root of this expression. And PT, we know it's total pressure, P is static pressure. Actually, we can measure PT and P separately through the pitot tube and also the static hole on the fuselage of the aircraft. So the pitot tube measures the total pressure and the static hole measures the static pressure. Then we can find the pressure difference. And you may notice I highlighted the density rho in red. And so you may already know why I do that, because the question is how do we get the density when the aircraft is flying? It's very hard. The answer is it's very hard. So we use the sea level, ISA sea level air density rho 0 to display the airspeed. So this airspeed is called the indicated airspeed. And why we use that? First of all, it's very hard to measure. The other reason, very important reason, is the dynamic pressure controls the aerodynamic forces on the aircraft, right? Because the lift and drag is related with half rho v square. That's the dynamic pressure. For example, since aircraft lift is directly proportional to dynamic pressure, an aircraft of fixed weight will store at nominally the same dynamic pressure at all altitudes. So if constant density is assumed, then an aircraft will store at the same ISA indicated airspeed at all altitude. So it's the other important reason. And if we look into the airspeed meter, and we can see the inside, and the second graph on the right hand side is how the pitot tube and static hole connected to the airspeed meter, and also on the bottom we can see the airspeed meter, and it has actually two dials. One dial is the indicated airspeed, IAS, and also it has true airspeed, which is relative to the wind, the speed relative to the wind. We know how the airspeed is measured, and on the airspeed meter, it's called indicated airspeed. And also we have other two terminologies to get familiar with. First is called the calibrated airspeed. So it's also as CAS. So calibration of the airspeed measurement system takes care of any instrument errors and position errors associated with the location of the pressure tappings relative to the aircraft flow fields, which will vary over the flight envelope. With these corrections, the measurement is called the CAS. This is called calibrated airspeed. So each airspeed meter will be calibrated. So what you read from the airspeed meter is actually the calibrated airspeed. And equivalent, the second is equivalent airspeed, EAS. Consideration of compressibility effects if applicable. So usually when the Mach number is larger than 0.6 and the altitude greater than 10,000 feet, and in these scenarios, we need to consider the compressibility effect. And the EAS gives what is known as the equivalent airspeed of the aircraft. So equivalent airspeed basically is taking the compressibility effects. So what is compressibility effects? That's when the density changes, because when we calculate the airspeed, we know in the square root we have a density rho. And if the aircraft is not flying very fast and not very high, the rho doesn't change. But when the aircraft is cruising at transonic speed, which is high subsonic Mach number or very high, the density changes when it's flying. So we need to take into account the compressibility effect. Basically, the density changes. Okay, it is called the EAS, equivalent airspeed, since it is the airspeed at sea level conditions, which gives the same dynamic pressure as that given by the true airspeed. And we can see the EAS, equivalent airspeed, is calculated by using the density at sea level, but the true airspeed, we need to use a local density, which is hard to measure, as I said at the beginning. Okay, we have the EAS and the TAS, so we divide each other. VES over TAS is a ratio of rho over rho their rho and a square root. Okay, and then we can find VTS. So true airspeed equals 1 over square root sigma times VES. So the ratio before EAS, equivalent airspeed, is ratio, and actually density ratio on a square root. And we know at the sea level, rho zero is larger than rho at the flight or during cruise. So this ratio is smaller than 1 because rho zero is larger, and which means true airspeed is larger or smaller than equivalent airspeed. It's larger than the equivalent airspeed. So once the aircraft is cruising at transonic airspeed and also higher at a very high altitude, so the equivalent airspeed, the reading of the speed meter is smaller than the true airspeed. This is actually what we've seen in the previous slide. In the example of the airspeed meter, there's indicated airspeed and also the true airspeed. In the previous slide, when we discussed about the equivalent airspeed, EAS, and we mentioned the Mach number. So EAS, we need to consider the difference between EAS and TAS. And that one important factor is Mach number. And actually, in the aerodynamic module, we must get familiar with what is Mach number. So Mach number is a comparison between the true airspeed and the speed of sound, A, at the flight altitude. So M, Mach number, equals VTS divided by A. So remember, there is a condition, the A at that flight altitude. What does that indicate? Which means the A changes at different altitude. Why is that? So because you can see the A speed, sound speed, A equals square root gamma RT. Gamma is a specific heat ratio of air, which is 1.4. This is constant. And also gas constant of air, and it's also constant, but the temperature, absolute temperature, in Kelvin changes at different altitudes, right? If you remember the international standard, ISA standard atmosphere, temperature changes across different altitudes. So the speed of sound varies with ambient static temperature, and it's indirectly altitude. That's why in the definition of Mach number, we have a condition at that flight altitude. So this is a calculation or definition of the Mach number. And finally, since we talked about the measurement of altitude and the measurement of airspeed, and here are a few units we usually use in flight and marine time. And first is a nautical mile. 1 nautical mile is actually 1 minute of an arc at the equator. So what is 1 minute of an arc? That's 1/60th of a degree. And then we have the conversion between nautical mile with meter, mile, and feet, and also meter versus mile. 1 meter is 3.2800 feet, and that's conversion. I'm not reading it. So mile is not used very frequent, but only in the UK and the US. So this imperial unit. Most of the countries now use international standard meter. And the third is knot. Knot is a measurement of a unit of speed. So 1 knot is 1 nautical mile per hour. And we need to get familiar with this nautical mile and a knot. And 1 knot is usually, we use this conversion, 0.5144 meter per second. So usually we should remember this conversion, 1 knot to meter per second.